All right, part A. Free body diagram for both boxes. This is box S, mass capital M, and the tension in the string is the only force acting on it because it's on a frictionless surface. For the other box, mass lowercase m, so tension is the same because it's on the same string, they're connected by the same string. Mass lowercase m, the reason that mg here is so much bigger than t here is because we know that the system is moving because this guy is called the sliding block, so obviously it's sliding. And the only way the system can move is this one goes this way, this one goes down, because there's no force here. And so if this goes down, that means that the force of gravity acting on it has to be greater than the tension in the string, which is why I drew it that way. And it's called block H because it's hanging. So that's part A. Part B, expression for the acceleration of the hanging block. You write out the net force equations for both boxes like this. So again, tension is the only force acting on this box, box S, and so it's just T equals capital MA. And then here, the line of motion of this box is going down, and mg is pointing down, and so that goes first, and then you subtract t from that to get lowercase ma. The reason the m's are the same is because they're connected by the same string, same tension, same pulley, and so they have to have the same acceleration. So to solve for the acceleration, I subbed in capital MA for t in the equation for block H, like this. So T equals capital MA, there's a T here, so just replace that with that, and you get this. Add this to both sides. Like this. And then you can just factor out the A. Like that. And then divide both sides by the total mass. So A equals mg over the total mass. All right, part C, expression for the tension. Okay, so again, write out the forces for both boxes. Like that. And then, no, never mind. In this case, it's just this one. It's just this one. It only wants it in terms of lowercase m, g, and a. So just this one. Just add this to both sides. mg equals ma plus t. And then mg minus ma equals t. Like that. Factor out the m's. And you get m times g minus a equals t. Part D, increasing the mass of the sliding block will have what effect on acceleration and tension? So increasing the mass of the sliding block, the block here on the table, it will lower the acceleration, because this is the equation for the acceleration. Again, they have the same acceleration. Both boxes have the same acceleration. And so if you increase this number here, which is what is proposed, the denominator of this will go up. And in a fraction, when the denominator is bigger, then the actual number is smaller. So if you were to increase m here, then it would decrease a. Whereas with tension, it would increase tension, because T equals this mass times the acceleration. If you increase m logically by the rule of multiplication, T will also increase. And so increasing the mass m would lower a and increase T. Part E. This one is the one with friction this time. Expression for the acceleration in terms of both m's, mu k, and g. So, again, draw out your forces, or write out your forces for both boxes. Tension minus the force of friction, because this is the box that's on the table, so the table has a force of friction acting against the box, equals capital MA. And then here, the equation for the hanging block stays the same because there's no other force acting on it. And then you can break Fk down into mu k capital Mg. The reason you can do that, the reason you can do this, is because Fk just equals mu k times the normal force acting on whatever object you're trying to find the friction of. And the reason that the normal force is the same thing as the force of gravity for block S is because there is no force in the y direction acting on that box. And so it's on the table, and it's pushing down against the table, and the table is pushing against it back up. There's no other force acting in this up and down direction, and so the force down into the table and coming up from the table have to equal the same thing. So the normal force is the same thing as the gravitational force of that box. And then the terms were both m's, mu k, and g. So we want to get rid of this tension, and we have this equation. So we just solve for tension here and then plug it in back here. We get that, right, and then just put it back in here. Right, you get this. And then with that, you add, yeah. Because we want to find A. And so get both terms of A on both sides. Factor out A. Like that. Factor out A. And then just divide both sides by the total mass. And then get this, and then you can factor out a G too on the top. And so you get A equals G times lowercase m minus mu k capital M over the total mass. All right, part F, derivative expression for tension. So again, write out the forces. Just like that. Same thing as last time with the friction. And then this time, what you can do, you can replace Fk with mu k mg again. So again, like that, or like that. And then what I did this time, since we're trying to find tension, what I did was I divided both sides by m here, like just got rid of this m, and then found a here, because we don't want it in terms of a, we don't want a in the equation, and so I just replaced this a with a here, with what a is equal to here. And so that looks like no, excuse me. Looks like this. Right, so just literally just divide both sides by m, and then put that for m here. Like that, just put that in here, and then just like simplify all this stuff. Right, so this step is just literally, because this is mg over m minus t over m, that's the same thing, and so the m's can cancel out and you just get g minus t over m here, right? And then distribute the, oh, just realized that's capital M. It's supposed to be a lowercase m over there, my bad. And then just distribute the capital M to that little parentheses thing, like that. So again, that was supposed to be a lowercase m, not a capital M. And then just distribute the m to both terms. So this is minus mg, and then this is minus mt, capital MT over lowercase m. And then again, we're trying to find tension, and so get all those tension terms on the same side and all the other terms on the other side. Like this, right? Just bring this over here, bring this over here, right? And then factor out tension. And then on the other side of the equation, you can factor out mg. Like this. Just factor out the t from both of these terms, factor out the mg from both of these terms. And now that you have t, you can just divide both sides by this. So t equals mg 1 plus mu k over 1 plus capital M over 1. Here we go. T equals capital Mg times 1 plus mu k over 1 plus capital M over lowercase m. That's part F. And then part G, the tension affected by the friction. So the tension will have to increase, because if there is friction acting on this block is on the table. If there's friction acting against it, right, then T will have to increase and get bigger in order to oppose the friction, in order to get this to move. So if there is a force acting against it, then the force acting in the line of motion will have to increase in order to continue in the line of motion. So, presence of friction, T increases. Presence of friction, that's Fk, T increases. Part H, draw the free body diagram for the boxes. I'll do both boxes this time, not one by one. Okay, so take a look here. This is the bigger box. Well, the bigger box, it's less mass, but whatever. This is friction, this is tension, like the last problem. But we have this little small arrow here, and this represents the contact force of the smaller box that's placed in front of it as the system is moving. So if the system is moving this way, which it is, then the small block placed here will naturally push this way, which is why there's that little arrow there of F lowercase m uppercase m, because it's from the box with lowercase m to the box with uppercase m here. And then the hanging block stays the exact same. Now for I, we're given the numbers, and then we have to calculate the acceleration of the system. So let me draw out the here. This is the system, right? This one is moving down, causing these to slide this way. And so we can actually imagine this, like reimagine it as one system that's like one big block and it's just moving this way. So we can like make it into a horizontal plane rather than like two-dimensional. We can just make it one-dimensional into a horizontal plane. Basically forget about the tension in the string because we're just finding the acceleration of the total system, and just take it as one big block moving one way. And so we can rearrange it like this. Right. So literally just fold this up, basically turn it into a horizontal. And then the only force that's acting in this direction, like pulling it this way, would be the gravitational force of block M, which is hanging, right? And so we can put that in there. And let me just label these boxes to H, and then S, and then we'll just call it S2. All right, so this is box S. We'll just call this box S2. That's a 2, and then we'll continue to call this one H. And so the only thing that's pulling it this way is mg, right? But then we also have the frictional forces from the table onto the two boxes, right? And so it's acting on this box, and so we have to account for that. And so the frictional force of both of those boxes is mu k capital Mg plus mu k lowercase mg, because again, you know, they're both boxes, and you know the whole thing with the y direction, Fn is the same thing as mg in these cases because there's nothing acting on it up or down. And so taking that, we can take that into an equation. Like this. So mg, which is the only force acting in the positive direction, minus the friction, the only force acting in the negative direction of the boxes, equals the total mass, which is 2m here, plus m, times the acceleration. And so if we want to find the acceleration, we just divide both sides by the total mass. Like that. Both sides by the total mass. And then capital M, get my calculator here, capital M is 2 kg, and then lowercase m is 3 kg. And then coefficient of friction is 0.18. And you get 2.5725. A is 2.5725 meters per second squared. And then calculate the tension. Okay. So with the tension, part J, tension. With the tension, let's see. We can just take the equation of the hanging block, right? T minus, actually no, mg minus T, excuse me, equals ma, right? And now that we know what acceleration is, we can just plug those values in. So mg minus T equals ma, and then plug those values in. So 3 times 1.8 minus the tension, switch that around, minus 3 times 2.5725, 21.68. So our tension is 3 times 9.8 minus 3 times 2.57, where's 2.57 is fine. T equals 21.68 newtons. Boom. Part K. Calculate the contact force. Okay, so with the contact force, we can look at, well, obviously the only blocks we can't look at are the ones on the table. And we can set up the equation for each of them individually, and then figure out which one we should solve for. We should use to solve for. All right, so let me just make sure I got it right. Moving that way. This way. Yeah. All right. So we have here the equation for both of these boxes up here. Capital MA equals, I put mu k mg first, so we'll just put a negative there. Mu k mg plus T, because it's the only positive force acting on it, minus the force of the smaller block against the bigger block, like that. And then with the smaller block, lowercase ma equals, again, negative mu k, lowercase ma, lowercase mg, excuse me, plus the force, the contact force between the two boxes, because that is the only force pushing this box forward. So it's positive. And so we can see that that's the easier equation to solve for the contact force. So we just add mu k mg to both sides. Like that. and then just plug in those values. Two point 2.57 plus 0.18 times 3 times 9.8, get 13. So we'll just call it contact. F contact equals 13 newtons. Just plug in, excuse me, let me write down the actual equation with numbers. 3 times 2.57 times 3 times. There. That, and then that equals 13 newtons. Let's see. Calculate, wait. Oh, no. If the system starts at rest, part L. If the system starts at rest, determine the speed of the hanging block the instant before it strikes the ground. Okay. So we now have the acceleration of the system, and so we can use that and put it into the formula for instant velocity. Vf equals Vi plus At. Like this. Right there. Right. There's no Vi, so Vf is just At. Thing is, we don't know what T is. So what I did was I actually used the Y displacement formula. 20 equals, again, there's no initial velocity, so we just need it. 1/2 times the acceleration, 2.57 t squared, right? So the Y displacement function, 20 equals, there's no Vi, so we don't have to write out that part. 1/2 A, which is around 2.57 times t squared. Solve for t. And 3.94. 3.94 seconds. Let me check that. Yeah, 3.94 seconds. And so we just plug that into the function. Vf equals 2.57 times 3.94. 2.57 times 3.94. 10.13? 10.14. We'll just say it's 10.14. So it lands at around 10.14 meters per second. Yeah, because we found the time and then plug it into this function up here, and then 10.14 meters per second. And then m. Oh wait, well m we already calculated the time, so 3.94. Just use the Y displacement formula. 3.94 seconds, and then sketch a graph. All right, so with these graphs, I didn't really know if you wanted the individual block, the hanging block, or the system, but I just did the system. So the x of t graph should look like this. Should look like that, starting from the origin, because the line of motion is positive. So if the line of motion is positive, then, you know, obviously the graph is just going to be positive. And so that's why it's concave up, going up, right? And then it's initially at rest, clarified by the past problems. And so that's why I just put initial position at 0 here. The v of t function, sorry, let me organize this mess of papers on my lap. Okay, so the v of t function should look just like that, right? V of t should just look like that, because v is the derivative of x, and the derivative of a parabola is just a regular slope line, like a straight slope, and so it should be just this. And then speed versus time, literally the exact same thing, because line of motion is positive. So like that, speed versus time, same thing because the line motion is positive. And then acceleration versus time is just a straight line, because acceleration is constant. It's 2.57. And then net force. All right. Skip to the future a little bit. Caught one of my mistakes. This is what F net looks like. Not whatever that is. F net is constant, just like acceleration, because F equals ma, and both m and a in this case are constant. So there's literally no possible way it could have a slope. My bad. F net is constant, just like a.